Okay. All right. So so this is joint work with Tung Hong and Aishwarya Thiruvengadam. And I'm Stefano Tessaro. So I want to say that both of my co-authors actually wanted to be here today, but they couldn't come because of visa issues. So you're stuck with me now. Okay. So we already had a very nice introduction to most of, at least the framework I'm going to talk about. But so we're going to talk specifically about authenticated encryption now, which is symmetric encryption, which is meant to guarantee both confidentiality and integrity. And the specific aspect we're going to be concerned with is its multi-user security, which I'm going to introduce in the first part of the talk. And I'm going to argue is a fundamental security goal to support large-scale adoption of cryptography. And so we have already seen this, but the way we think here about authenticated encryption is as a deterministic encryption scheme where encryption for a particular secret key also depends on a nonce and potentially some additional authenticated data, associated data, which needs to be authenticated. However, for most of this talk, I'm going to omit the authenticated data because everything will extend to it and it just makes the notation a little bit more cumbersome. And an important point here, since encryption is deterministic, is that if we want to have security, we need to have every individual encryption depend on a different nonce. And otherwise, very bad things are going to happen and security can fall apart. Now, as we have already seen, authenticated encryption is a fundamental component of secure communication protocols, and in particular of TLS. And where after the handshake, we end up with a secret key shared between a client and a server, and which is then used within the record layer, in particular for authenticated encryption. But one particular aspect when we want to validate the security of such protocols that are used on a large scale, like TLS, and that we're going to focus on here, is that we have to be concerned about very powerful attackers that can assemble large amounts of internet traffic. And I'm thinking here specifically about state actors or a large network of compromised machines like botnets and so on. So we have known the NSA for many years, to more than a decade, of being capable of placing interception gears at the endpoints of internet backbones. And we have countries like China that can essentially filter every connection which goes out of the country. And so if we want to look at such attackers, so one concern is that they can mount cryptanalytic attacks that leverage access to large amounts of encrypted traffic and to their advantage. And we want to be as conservative as possible when designing cryptography. And one specific goal we're going to focus here is we want to make sure that if such an attacker wants to compromise any of the session with no clear preference which one of the sessions the attacker wants to compromise, then we want to have even that task to be as hard as possible. And this is exactly the target informally of the notion of multi-user security, which was introduced by Bellare, Buldurieva, and Micali in 2000 in the context of public key crypto. So here we extend this to symmetric key crypto. And here note that the term user is a little bit weird. So what I mean by a user is not an endpoint of a TLS session. It's really the session itself or the associated key. Okay. Now, why can this be a concern? So we can look at a simple example now where we have a web server that has some public file available, say an index.html file, that it delivers in an encrypted form to, say, different clients. And in particular, it uses the same encryption scheme, just independent keys in the same nonce. Now imagine the adversary can intercept all of the U resulting ciphertext and want to compromise just one of the keys with no preference which one of the different sessions. What the attacker can do is he can just try different key guesses, say P of them at random, and then he checks for every one of them. He just re-encrypts the index file and then checks the result against the U-intercepted ciphertext. And if it succeeds in one of these trials, then the attacker is pretty likely to have found the key of the corresponding session and can then decrypt later traffic that might be more sensitive. And so if you look at the advantage or the success probability of this attack, you'll see that you have P trials, and each one of them you have roughly probability U over 2 to the K of succeeding in finding the key. So the overall probability is P times U over 2 to the K. And K here is the key length. So if, for example, we have P to be equal to 2 to the 64, which is at the boundary of what we would consider feasible, and K is equal 128, we can see clearly a difference. So if the adversary targets one single session, so U is equal 1, then the advantage will still be very tiny, so 2 to the minus 64 success probability. But if the attacker can assemble, say, 2 to the 64 ciphertext, and with a similar computing effort, now doesn't care which one of the keys it recovers, then suddenly the advantage goes up to 1. So it is a substantial difference if you allow assembling such multiple ciphertext or not, and you don't care which session you want to compromise. So the reason this is happening is because we are encrypting the index file with the same nonce over and over. And this comes from the common practice of just picking nonces as counters, which is kind of historically rooted. And so you can really check a key guess against all of the potential ciphertext. And as this was already pointed out in the previous talk, the developers of TLS 1.3 actually realized this and proposed a kind of neat solution to this, which is very cheap. And essentially, what they do is they still use GCM as their underlying authenticated encryption scheme, which is the most widely adopted AE scheme today. But what they do is that for every session, they establish an initial nonce randomizer, which I call K prime, so on a per session basis. And then whenever they want to encrypt with a nonce n, which you can think of as a counter, they instead invoke GCM with the underlying GCM with nonce n XOR K prime. So it's not quite the right picture formally because it's an XOR instead of a plus, but you can think of this as choosing an initial nonce value at random and then just counting from there. And currently what you get there is that for every individual session, what you're going to get is that so for every individual nonce, the number of sessions that are going to reuse the nonce is one or a very small constant depending on how many sessions you're looking at. And so the previous attack kind of fails because now you can check only against one or very few ciphertexts. So you will conjecture here that the advantage is independent of the number of users or sessions, so something like P over 2 to the K. So this conjecture has guided the development of TLS 1.3. And in fact, if you read the RFC, you'll see that there is actually even a reference to an analysis of this scheme. And the paper in question is a very beautiful paper. Actually, I should say that I will refer to this particular scheme. You can think of it as a different authenticated encryption scheme with a large key, and I'll refer to it as RGCM. So, and the paper in question is a very beautiful paper by Bellar and Tachman that introduced the whole topic of analyzing the multi-user security of authenticated encryption. But if you look at the paper in detail, you'll see two things that are kind of a bit concerning. The first of all one is that the quantitative guarantees that they give on the security of RGCM and also plain GCM that they study there are somewhat weaker than what we would expect heuristically. And on the other hand, for RGCM itself, they only show a security improvement over plain GCM in the case where the attacker doesn't try to compromise integrity. Obviously, we care about authenticated encryption, so integrity is fundamental. So this is kind of a non-obvious gap which has been there in the validation of TLS 1.3, which the RFC suggested this is done, but actually this hasn't been done completely. So this is the gap we aim to close, and the way we do this is by giving a new security analysis actually of plain GCM. So we revisit the security, but we're going to do so in a model that considers a somewhat different and unusual quantification of adversarial resources. And from that, we're going to be able to get a tight analysis of the security of RGCM. So in this sense, this completes the picture by showing for the first time that the authenticated encryption in the record layer of TLS 1.3 achieves what we expect it to do. It also easily extends to other ways of randomizing nonces that have been used implicitly in TLS 1.2, IPsec, and other protocols. And also, the bounds are quantified in a way that they also make obvious the advantages of rekeying when using authenticated encryption in the multi-user setting. And I mean, likely there are more applications because GCM is used all over the place, but this is what we focus on. All right, so in the rest of the talk, I want to talk a little bit more about GCM in details. So you won't need all of the details for the type of things I'm going to tell you, but just to give you an idea and the prior work, and then tell you about our results and the applications, and then some concluding remarks. So in particular, I mean, among developers, so GCM is known as something quite tricky to implement, but if you abstract it, it's actually not very hard to understand. It's kind of an instantiation of encrypted MAC, essentially, where you want to encrypt a message with a nonce n, and then what you do, you first split your message into blocks and then apply counter mode encryption to encrypt the message with counters derived from the nonce, and then you authenticate the resulting ciphertext with essentially a nonce-based Wegman-Carter MAC that uses some underlying extra universal hash function. Again, this is just a very simple hash function that can be done very efficiently that only satisfies some weak combinatorial properties. And GCM specifically uses something called ghash that only relies on essentially one finite field multiplication per ciphertext block and is really, really fast. Right? So the final ciphertext is the counter mode ciphertext plus the authentication tag. And what does it mean here to be secure? So in the multi-user setting, we can just extend the traditional security notions of real or random security to handle multiple users. So we'll do so by having a real world where multiple independent keys are associated with each of the users. And for confidentiality, the adversary will have access to an encryption oracle that allows you to encrypt a message and a nonce arbitrarily for a specific user. So this is going to be encrypted with the corresponding key. And this is compared with an ideal world where the encryption oracle just returns random ciphertext of the right length. And here, since our schemes are using a block cipher, we will model this block cipher as ideal. So this is often the case in such analysis. So it's just a randomly chosen block cipher to which the adversary has query access. And the adversary will have to decide whether it's in the real world and the ideal world. Each can occur with probability 50%, and we'll check whether it succeeds or not. Now, obviously, there are easy ways to distinguish. So we will look only at nonce-respecting adversaries that will never reuse the same nonce for the same user. Otherwise, it's easy to tell apart the two worlds. And for integrity, we can just enhance this definition by adding a verification oracle, which in the real world checks validity of ciphertext. In the ideal world, it just always say false, unless we're obviously submitting to it a ciphertext which was honestly generated from the encryption oracle, in which case we know the ciphertext is valid. And now the way we measure security is through the advantage of the adversary. We just measure quantitatively how much better than guessing with 50% probability the adversary will do in telling the real world and the ideal world apart. So the game we are playing here is that of concrete security. So we have an adversary and we want to upper bound its advantage as a function of its resources. Now, for example, Bellaire-Tachman extended previous bounds for single user security by Ivat et al. To plain GCM. And so they gave a bound that consists of different terms and depend on different parameters, in particular on the block length of the block cipher, on the key length, so N and K, and also on the number of users for which the different users for which the adversary makes queries, the amount of offline computations, which we model as ideal cipher queries here, and a parameter sigma, which is the overall number of encrypted blocks and verified blocks by the adversary. And this bound was later improved by Lux, Menink, and Patterson, essentially removed the factor U in front of the second term. And to give you a sense what this bound really means, so if we set N to be equal K equal 128, as it is often the case, then we see that the first term essentially tells you two things, namely that the number of users or sessions can be at most 2 to the 64, otherwise there's no security guarantee, and also that there's a trade-off between the number of users and the amount of offline computation, so their product should be at most 2 to the 128. This corresponds to the attack we have seen before in my motivation. And also the second term tells us that the overall number of blocks cannot exceed 2 to the 64, otherwise we lose any security guarantees. Right. So now for our GCM, so Bellaire-Tachman also have shown a bound which was meant to show an improvement, but somehow the bound is kind of a little bit more complex than you will expect. So in particular, there's a first term that is kind of better than what we had for plain GCM. There's a second term which is worse, but fair enough, they haven't improved the bound with the techniques from follow-up work. There are some other terms that I'll talk a little bit more about later maybe, but where it's kind of not clear. So it depends a bit on the parameter. They're usually better, but they're not leading terms, but depending on what you have there. But most crucially, their bound really holds, these improved bounds only holds if the attacker doesn't make any verification queries, which is a major drawback. So we want to clean up this and give a better bound, a clear bound, and also try to allow for verification queries. Right, so how do we do this? So we do this by giving a new, more general bound for plain GCM. And we're doing this by using a different parameterization of the adversarial resources. In particular here, I want to make a very important point. Namely that actually the previous work, the work by Lux et al., gives a bound for GCM that is actually tight with respect to the type of parameters the parameters they're looking at. So the bound we've seen before is tight. And if we look why it is tight, we'll see that the different terms arise, so are matched by different attacks. And so the first term is essentially matched by an attack that where you re-encrypt the same message, which is same nonce for different users. The second term is matched by an attack where you encrypt sigma blocks for one individual user. Now, what's the catch with that? So this might be true in general, but if we look at the usage of GCM, these attacks might not be feasible just because of the way in which GCM is used. So for example, if we use GCM within our GCM, because of the way in which nonces are randomized, you might not be able to perform this attack because you don't get to invoke GCM on the same nonce that much. And similarly, the second attack might not be feasible because you might target a large sigma, but your implementation might actually ensure that you rekey often enough that you never get to encrypt more than, say, B blocks for some variable B, which is controlled by the users. And so you might not get to encrypt that much with a single user. And so again, this might not be a problem. So there's just an important general message here pedagogically that tightness is always with respect to whatever parameters you put in. So if you add different parameters, you might have a different viewpoint. So what we do here is we actually consider another parameter, which we call D. This actually came up in a recent paper we had with the partially overlapping co-authors here, which was analyzing AS-GCM SIV, which is a different authenticated encryption scheme. And there we realized it's convenient to introduce a combinatorial abstraction of nonce reuse across users, where we have a parameter D that captures the number of users that will reuse any particular nonce. So no more than D users. And this is only in encryption. So we don't make any assumption on verification queries and how much nonces are reused. And you'll see why in a second. And so in a way, you can think of GCM within RGCM as a way of ensuring that you have a sufficiently small D when invoking the underlying GCM. And so we prove a bound here that extends previous work, and it's now parameterized by this D. Also here, Q is the overall number of encrypted messages, so it's slightly different. And I'll come back to this first term, but we also improved the second term. This is where the rekeying comes in. To be instead of sigma star, a sigma square, you will have a term as sigma times B. And this B is a bound of the number of encrypted blocks per user, not verified, just encrypted. And to see why it's advantageous, you can consider, for example, a setting where you will actually force every session to encrypt almost 1 terabyte of data. So there will be 2 to the 36 blocks, if I did the math right. And so you'll see that if you do that, now you're not limited to encrypting overall 2 to the 64 blocks, but you can actually go up to 2 to the 92 blocks and still get meaningful guarantees, right? So that's where you see that, rekeying makes sense, at least from this perspective. Also, with respect to the first term, if we go back to GCM is used within RGCM, we can actually prove bounds on the actual resulting D. So we can see that if we randomize nonces as within RGCM, that we can think of invoking the underlying GCM. And if we look at the maximum number of users that use any particular nonce, we can use a combinatorial balls into bins lemma that actually shows us that as long as the number of encrypted messages is not larger than 2 to the R, a little bit less, where R is the nonce length, so 96 bits, then no more than a constant number of users will reuse any particular nonce value. And so this will give you directly a bound, right? So for example, for R96 and Q smaller than 2 to the 88, our D will be 15. And so you will get a bound that look like this. And of course, we can compare it with the Bellaire-Tuchman bound. And we see already a few interesting things. So for example, the Bellaire-Tuchman bound inherently tells us, even disregarding the other terms that are worse, that we cannot expect to have security beyond 2 to the 64 users. So this is 2 to the 64 intercepted sessions in a large-scale attack. So our bound doesn't have any such limitations. And also, if you look at the rest, even ignoring the second term that could be optimized, there's different parameter regime. Say, you have a large P, a large sigma, and U might be smaller than 2 to the 64 still, where the lower bound, the lower upper bound doesn't give anything as a guarantee, but our bound still gives guarantees if we limit the number of data which is encrypted per session. Now, obviously, you can so one thing here is that there's this constant here which is a little bit weird. Aesthetically, it's very unpleasant, 243, and it actually seems that looking at the other bound, it's because of the P-dependent term, you might be able to improve it. And actually, we believe so. But there's a one important thing I haven't told you yet, which is that actually our results show something way more general than what needed for RGCM. And in particular, our bound holds even if the nonce randomizer K prime is made public, which was not the case it's not needed for RGCM, so it's part of the handshake, but actually we don't need that. And this might be useful in other applications where you don't get that for free. So I think you can reduce that constant if you make it private with actually a simpler analysis, but you expect to gain like 3 bits of security. So we didn't do it in the camera ready version. And also, so you can analyze other things. So something we realized, at least by reading RFCs after a little bit, is that other protocols and also TLS 1.2 already had some nonce in the GCM cipher suite, and already some nonce randomization in place. And that essentially you will randomize the beginning of the nonce, the first 4 bytes with a salt. And again, you can derive bonds from that, which obviously are worse than RGCM. So just running out of time. So the proofs, I'm not going to tell you anything. So I was planning to run out of time. Now, so they are quite involved in, they use H-coefficient method, which is a common technique for this type of things. Just to conclude, so there are really 2 lessons learned. So this is, I hope it's a good news talk for most of you. So the first thing is that nonce randomization is really useful. So you should care about multi-user attack. Maybe that's lesson 0. Lesson 1 is that nonce randomization helps you, and it's done right in TLS 1.3. Other protocols implement some form of it that achieves something. It's cheap, so you should do it. If you already have key exchange in place and you can output a slightly longer key, you can just get the randomizer from there. And the other thing is that obviously rekeying introduces other attack surface that you might exploit differently, but at least from a multi-user security perspective of symmetric crypto, it's worth a rekey and make your session just more often you make security better. Okay, thank you. So the paper should appear in ePrint anytime now. So, okay.